We're going to go over strong acid, strong base titrations first. That's because, relatively speaking, this is the easier one. So our objectives, we'll learn the difference between strong acid, strong base titrations and weak acid or weak base with strong base or strong acid titrations. And we'll define the equivalence point and the half equivalence point. The vocabulary to describe a titration is in general the same between acid, base, and redox titration. The titrant is in the burette, the analyte or titrand is in the flask. We can make a titration curve for acids and bases by graphing pH versus the volume of titrant added. Titration curves for acids and bases can be divided into 4 different points where the type of calculation used to calculate the pH changes. The first region is at the very start of the titration. At this point, the pH is equal to negative log of H plus the titrand. In a strong acid base, this is just straightforward. You do negative log of the concentration because it fully dissociates. But a weak one, you have to pull out a nice table. For the second point, that is the half equivalence point on this graph. At that point, the HA concentration is equal to the A minus concentration. So if you have a weak acid or base, this is the point at which pH equals pKa. If you have a strong acid, strong base titration, then you just use subtraction and you figure out how much acid or base that you started with you have left. The region just after 1 to before 3 all uses the same mathematics. That's when the amount of titrand is less than the amount of titrant. I take that back. The amount of titrant is less than the amount of titrand. Anyway, point 3. What's going on there? It's the equivalence point, where the moles of acid is equal to the moles of base. This is true even for polyprotic acids, but it is only true for one species of the polyprotic acid at a time. So for example, if you titrated sulfuric acid, you would see 2 separate equivalence points. The first one would be for H2SO4 in equilibrium with HSO4-, and the second one would be for HSO4- in equilibrium with the sulfate ion. Finally, anywhere after the equivalence point to infinity, you can use the same math for determining the pH. You determine how many moles of titrant was used up, and then you determine the pH from there. There is a particularly important aspect to all of these calculations to remember, always. The pH is dependent on the concentration, and you are constantly adding more volume. It is often easier to calculate using a BCA table in moles, and then figure out the H plus present, finally put it into an ice table or the Henderson-Hasselbalch equation, depending on the situation, to get your answer. Note that the pH of the strong base starts high and goes low, and the pH of the strong acid titration starts low and goes high. And for both cases, at the equivalence point, the pH is 7 for a strong acid, strong base. So let's take a look at some important features on a strong acid, strong base titration curve that will help you to visually identify it if you have that type of titration versus a weak acid, strong base. So the pH is generally lower at the start for a weak base and higher for a weak acid, though not necessarily, because that's completely dependent on concentration, right? So if you have a very low concentration of strong acid versus a very high concentration of weak base, those two can cross. In all cases, the strong acid, strong base has a flat line going from the start. So the slope is consistent when you go across here at the very beginning. The strong acid, strong base has an extended sharp part to the slope. It's a very tall part. The pH at the equivalence point is always 7. This is the most salient feature of a strong acid, strong base titration, and it's the thing you should look for first. And finally, the pH after the equivalence point eventually becomes asymptotic with the concentration of the base or acid used as a titrant. And the reason for that is you're slowly approaching the concentration of the thing that you're titrating with. You've used up all the acid or base. The only thing left is your titrant. Okay, so now we have an idea of what to look for. Let's compare the two head to head. Let's do a direct comparison between strong acid, strong base and weak acid, strong base. At the start of the titration, strong acid, strong base gives a nice straight and flat line. Generally speaking, the pH of the weak acid will be higher than the strong acid. If the concentration of the weak acid is particularly low and the weak acid is high, this may not be the case, but in general, it will be. The weak acid strong base has two different slopes at the beginning. So we have this region where you go from 0 to 10% of the equivalence point. It has a steep slope, and then after that it kind of flattens out, becomes more shallow. As you add base to your weak acid, you make anion. And what does the mix of a weak acid and a conjugate base make? Yeah, that's right, it's a buffer. So that's going to prevent the pH from varying much. So once the buffer forms, the slope becomes much flatter. Also, your math becomes much easier, but we'll get into that in the next presentation. Not the ones for today, but the ones for Friday. When you near the equivalence point, both titrations, the slope rapidly increases. At the equivalence point, where acid equals base, you can see that the pH of the strong acid, strong base is 7, but for the weak acid, weak base, it is greater than 7. Why is that? Because the conjugate base is present, and it is actually going to go back the other direction. You'll also note that in this high slope region, it takes up more space for the strong acid, strong base than the weak acid, strong base, as previously stated. And finally, after the equivalence point, both of them become asymptotic with the pH of the base, but the weak acid curve takes a little bit longer to get there. All right, so at the start of the titration, for a strong acid, the concentration of the acid is equal to the concentration of H+. If you take the negative log of the concentration of H+, or if you have a strong base, 14 minus the log of the base, you'll find the pH of that point. It's nice and straightforward because you have 100% dissociation. In the region from right after the first drop is added until you get to the equivalence point, the titrand is greater than the titrant. So it's easier to convert into moles, and you're continually adding volume, which is why that is easier. You do the difference between the moles of titrand and titrant first, and you should have excess titrand when you're done. And when you have excess titrand left, that means you have H+ left, so you do negative log of the H+ left. And that is your pH for that region. At the equivalence point for strong acid, strong base, pH is 7. You don't have any calculations, it just is. It's nice and easy. All right, so after the equivalence point, the titrand is now less than the titrant. So you have gone past, you've got just titrant going on. It is easier to do these problems if you convert to moles and you're continually adding volume, so you're going to constantly have to calculate the new volume. So you take the difference between the titrant and the titrand, and that will give you probably an H+, right, if you've got a strong acid that you're titrating with, and it will give you an OH- if you have a strong base. But either way, your pH is always the negative log of the H+ concentration, so just use your KW to figure it out if you need to. To summarize, at the start of every titration, everything is titrand. Before the equivalence point, titrand is greater than titrant, and so you're going to have to do a BCA table and then figure out your molarity in order to determine pH. At the equivalence point, acid equals base, and for a strong acid, strong base, that means that the pH is 7. After the equivalence point, titrand is less than titrant concentration, and so you're going to do another BCA table and then find the molarity from there.